Hi, everybody. Good afternoon. I'm introducing Mike Lockwood. Mike Lockwood produces mirrors, and he's an audio engineer, right?
Electrical engineer. Originally, yeah.
And I like him because no, he likes Rush, right? We like Rush.
Smart. Okay. Well, we've got a little bit of the Keys weather back now. It's nice. You're like starting to warm up a little bit. So we want to talk about thermal effects on optics and telescopes. And I'm going to go through a bunch of different things. Some stuff you may have seen, some stuff you may not have seen. But we're going to try to quantify some of it and make it kind of bring it into the real world as to when it might affect your optics, and you may not know it. There's certain weird things that can happen. So why is an optician talking about thermal effects? Well, it's because I get blamed when things go wrong in telescopes, naturally. So it's entirely selfish. You know, I'm the first person they call. So by sort of a strange coincidence, now I've had to learn what goes wrong in telescopes, and I help people debug them. You know, if I'm working with a client on a telescope, that's part of what I do. I kind of give them advice about how to use the optics and maximize their performance. So pretty much covering my butt by figuring out what exactly is happening. So with all this going on, mirrors of small to very large size, I kind of wanted to identify the main problems, the main phenomena, and give solutions to people. And this is still due for an article. I haven't had a chance to write this article with all this stuff, but eventually I'll get there. So again, telescope users tend to blame the optics. The rule is if it's really obvious, like smack you in the face obvious, it's probably mechanical, unless something is really broken. So this talk, we're going to look at the effects of temperature change on structures and the glass, and within the optical cavity itself, the space of air that the light is traveling through to get to the optics. So these temperature changes, which, you know, typically a mirror is cooling down and a telescope is cooling over the course of a night. So that's pretty much what I'm going to talk about is cooling effects. There are heating effects, but they tend to be the opposite. And when that happens, our optics do up, and we just are, you know, we kind of don't care at that point. So the telescope dimension changes. Imagers know this. You may have focus shift due to that. And also the mirror cells change size as things cool off. Everything generally shrinks. There are disturbances of the air in the optical cavity. That's the air the light is coming through. And then there are unintended issues depending on tolerances held in the optical mounting and some other things that you wouldn't expect. So typically just about everything on Earth expands as it warms up, except for very rare things. Water to ice is completely different because it's changing phase. The ice actually spans. So we don't have to worry about that, hopefully, with a telescope. Our materials are just generally expanding as they warm, and cooling, they'll contract as they're cooling. So we have this quantity called the CTE, the coefficient of thermal expansion. All it tells you is how much something expands and contracts given a temperature change. So if you know that, you know the material, you can calculate how much it's going to shrink or expand for a particular change. Most of the time, this is assumed to be linear. So we're going to assume that it's proportional to that CTE. If you go off into the extremes of cold or heat, it may not behave linearly, but we're not going to worry about that, and we generally don't have to. So CTE is typically expressed in parts per million, per degree of C, or sometimes per degree F. So a material is going to change shape by this fraction of amount, this parts per million, for a given temperature increase or decrease. Okay, there's a little bit of math. It's not that hard. Don't worry. Have some coffee. Hug a friend. If you see someone in distress, just make sure they're okay. So we have pretty simple formula. This is a change in dimension. This is a change in temperature. This is the dimension of the object. So remember, this is proportional to the size of the object. So we're talking about a railroad track that's 100 miles long. That expands 100 times more than a railroad track that's 1 mile long. And so just keep that in mind. So telescope size matters for that as well. So all we've got is the change in dimension is the CTE times the change in temperature times the dimension. So again, proportional to dimension and these other quantities. That's all that says. Or you can re-express it in this form here. Simple. So here are the CTEs. Anybody seen these before? Mechanical? Yeah, okay. So we make a telescope out of wood, generally, depending on the kind of wood, and it depends on the grain and the humidity and everything else. There's lots of stuff going on with wood. But generally, I think the more stable stuff is about 50 parts per million per degree C. And if we have a dimensional change over here, we have about 10 thousandths of an inch per foot, which is significant. So you can measure that pretty easily for, I believe, a degree C is what I calculated that for. So if your wood warms up 1 degree C, it's going to expand by about 10 thousandths of an inch. Aluminum is less than half of that, about 23 parts per million. So you get 4.6 thousandths of an inch expansion per foot per degree C. And these are dropping. These are materials that expand less. 11 parts per million for carbon steel. Steel expands more than less than aluminum. So if you're building a telescope and you have tight tolerances to hold, you might consider using lighter weight, like thinner steel rather than aluminum. It's harder to machine steel, but you might consider that. Plate glass, now we're into the glasses, is just a little under that at 9 parts per million. And this is why typically now opticians and telescope companies have sort of transitioned from plate glass to something that's lower expansion, like borosilicate, but not always. A lot of the import glass now is crap. It's poorly annealed, but it's just kind of pot glass, so you never really know exactly what it is, and it's probably around this plate glass CTE. So borosilicate, like Pyrex Supermax, is just over 3 parts per million. So we're talking about 6.5 10,000ths of an inch of expansion per foot per degree C, just to give a little bit of a perspective. And then we get down into Invar, which is a common metal used in optical instruments because it has very low CTE at only 1.2 parts per million. Quartz is less than half of that, at about a half. Carbon fiber, depending on how it's laid up, maybe around 0.2, maybe a little more. So carbon fiber and glass actually can match fairly well together. So we'll talk about that in a little bit. Zero dur, 0.02 parts per million per C, but dollars per pound is very high. So we generally don't use it, but it's really nice. And there have been some others over the years. So let's look at a 12-inch mirror cell made out of different materials. If we have a 30-degree drop in temperature, the cell is going to shrink by about 5 thousandths of an inch. Okay? The mirror is going to shrink in diameter by about 0.6 thousandths of an inch. So we have not quite a 10-to-1 ratio there, but pretty significant. So we've got about a 4 thousandths of an inch difference between the glass shrinking and the metal shrinking. So when you have a mirror in a cell that's very tightly constrained, there's not a whole lot of extra room around the mirror, you want to make sure that for that given temperature drop you have about 4 thousandths of an inch clearance, because the cell is going to shrink more than the glass. And it will get tighter and tighter and tighter, and in wintertime this can be a big deal. However, the metal is also going to shrink faster because it gives up its heat more quickly. So it's going to shrink more quickly than the glass at first, so it might pinch it, and then the mirror might catch up depending on how much room there is around the mirror. So weird things can happen. What I'm showing, you can't see it, as I'm going to talk about a 50-inch f4 steel telescope that a friend of mine uses for asteroid position measurement. His name is Bob Holmes. He's done a ton of these measurements, tens and tens of thousands. So 50-inch f4 cellular mirror. In steel, when you have a 30-degree temperature drop Fahrenheit, the cell is going to shrink by about 9 thousandths of an inch. Okay, so you can actually see that with a feeler gauge over that temperature drop. The mirror is going to shrink by almost 3 thousandths of an inch, so the difference is about 6.5 thousandths again. So we want a little bit more than that, just in case the metal is going to cool quicker. So generally you want to say about 10 thousandths of an inch so that mirror is not pinched. However, with friction and everything else that's going on for such a large, heavy mirror, you may have other effects when it's sitting on its edge, it's up against the metal and the metal's shrinking, it may pull on the glass temporarily. All kinds of strange things go on. So in this case, minimizing friction for certain types of edge supports may be important. So anyways, what we're talking about is about a 64th of an inch if you're talking about an aluminum cell for this particular size, for something about 50 inches in diameter. Then think about if you're gluing a mirror to something. What do you need to pay attention to? How much they both shrink and how much the glue can flex. So generally I recommend not gluing mirrors because you can have a lot of problems, and partly again that's selfish. But if you know what you're doing and you do it in a way that the glue can actually flex, it can actually work fairly well. And there are entire books that have been written about mounting mirrors and lenses, a lot of which involves mounting lenses, and carefully adhering them in a certain manner that they are not warped as the temperature changes. Book by Yoder, Mounting Optical Elements, I believe. I read it, it's about that thick. It's pretty interesting, but mostly geared towards lenses. There is a section on large mirrors. We tend to let our mirrors float so that the cell can expand and contract, and usually this won't pull on the mirror too much and it won't distort it too much. One trick, if you ever see weird things going on, is just point the telescope straight up and give it a shake. Let everything kind of unstick. You occasionally get friction in the cells, and sometimes that'll fix a lot of things. Mirrors stick to their supports, and the reason it becomes a problem is because of the expansion and contraction. It doesn't take a lot of force to bend glass. That's one of the key things to realize, especially when you're, I will show a video if we get power back here, if we figure out a way to do this, of glass actually bending due to thermal changes, due to the heat distribution within a mirror being transferred to another mirror, and eventually they come to equilibrium. That's a flat mirror. So if you're gluing a mirror to something, you want to match that material, carbon fiber, maybe Invar, as close as you can to the actual piece of glass that's being adhered. So focal length change in these types of telescopes is proportional again to that CTE. So if you have a 12-inch f4.2, let's say it's a 50-inch focal length, and we have a 30-degree temperature change, if it's Pyrex, the focal length of the mirror is going to get shorter just due to the mirror literally shrinking by about 2.7 thousandths of an inch. Aluminum will change in length, the telescope tube, by about 19 thousandths of an inch. So there we have a difference of about,
Power's out for a little while.
okay, 17 thousandths of an inch. And so the imagers know this well, and some of the better imaging telescopes will be designed to be athermal, or they have focus compensation for temperature. If we're doing steel, we have a change in dimension for the steel, 50-inch long, roughly of about 9 thousandths of an inch, so the difference is about 7 thousandths. Invar is about 1 thousandth, so maybe 1.7 thousandths of an inch difference as this thing cools off 30 degrees. And Zeradur and carbon fiber, let's say, there's almost no change at all. So ideally, if we could have that for everything, that'd be wonderful. I decided one day to do an experiment. I had a 5-inch flat, it's Pyrex, and I heated it up under a heat lamp for about half an hour, so it got fairly warm. I have a 10-inch Zeradur reference flat that I could set it on, and what happens is, of course, the warm mirror transfers heat to the Zeradur, and slowly they equilibrate to the same temperature. So I set up a time lapse, 4-second exposure taken every 30 seconds for 2.5 hours. Made a time lapse out of it. Started it up, I went out and mowed the lawn, came back and made a video based on 75 minutes. So what's going on? I'll show the video in a second here. So we have this flat, it's an elliptical flat, so it's 45 degrees, like I use in my 12.5-inch night vision scope that I've got here. Okay. So it's a little oddly shaped, but what happens is,
Power just came back up.
okay, cool, yes. So we have this glass that is going to transfer heat, and when it does that, due to the uneven heat in the glass, it will warp because it has a CTE. It has a CTE. So that's an interference test of a flat that started off really warm and ends up reasonably flat. I'll play it again. Okay, so we have all these bullseye fringes, which they're like a contour map. I've done a talk about interferometry. So we have basically a surface on the flat that's concave like this, and those interference fringes are half a wave each. So that's the difference between the flat mirror that's not distorting and the Pyrex mirror that is. It's many waves. And then we let it cool off over time. How long? This was about 75 minutes. And then we have a fairly flat mirror. It's not perfect, but it's pretty good. So what I actually have here, to make sure I get back to the same slide. No, it didn't do the same slide. I think I have to hit shift. Okay. So we actually had, it actually started out about 10 waves concave. If you go through and count all the fringes, you can figure out how much the peak to valley is. And it ends up around a quarter to a half a wave, depending on how you're looking at it. So most of the change in this mirror, which was probably about an inch thick, but it was quite warm. I did it for maximum effect. Most of that change was done in about 40 minutes, and this is just a simple interference test setup with nearly monochromatic green light, specifically done for flat testing. So that warm flat transferred its heat. It was temporarily distorted in shape as the bottom part got cooler quicker, and then the heat transferred through and it went back to its usual shape. So this happens in a mirror every night. Every night, especially after it's been out in the hot Keys sun here, maybe under a cover. That mirror is going to go through distortions just due to heat transfer into the air. Rather than, this was almost directly to another material, so it's faster, but into the air is slower. We'll talk about that coming up, why we need fans. So changing air temperature is important for testing. We need the air to be fairly stable. We need the temperatures to be fairly stable for a period of time to get an accurate optical test. You can actually get an erroneous, or you can fake a test by taking a picture of the fringes if they look good before the equilibration is done. So you got to wait. You've got to be conscientious and make sure that everything is good. So to make an optical test good, we need stable air temperature, stable substrate temperature, and a good reference flat, and honesty. The secondary mirror with a heater on the back, which many of us have for dew heater, will go concave slightly because the back expands and it kind of does this. So we want to minimize that, but it does happen. Yeah?
What about the heater you can get for SCTs on
the heater around the corrector plate, since the corrector plate is thinner, I don't think it has as large of an effect. I mean, there's also much less sensitivity optically to the corrector than a mirror. The corrector can be bad and the telescope will still work fairly well. So those distortions don't really affect things much.
So that dew heater is not affecting that plate, right?
Not nearly as much as it would a mirror. Okay. Yeah. Again, it depends on how it's set. I've seen secondary mirrors go astigmatic because the secondary heater was turned way up, and as soon as you let it cool off, the astigmatism goes away. So primary mirrors take longer to cool just due to their massiveness. So that's why light-weighted mirrors are popular with professionals. It's unavoidable due to the mass and the nature of the glass. And quartz and Supermax, Pyrex, they all cool about the same rate. They give up their heat at about the same rate. Though quartz, with its reduced CTE, it's about 6 times less than Pyrex. It distorts about 1/6 as much. So quartz is a good thing. This is only temporary, right? So as soon as we equilibrate, like this is one of the few places that I've been where you can actually equilibrate an optic, because the temperature typically drops to about 70 degrees and stays there under normal conditions here, not like previous nights, but like tonight. So we generally don't have a huge delta here. The optics can actually equilibrate and get to the point where they are their true shape and they're not distorted by cooling. So this is why we can also oftentimes use a really high magnification here. You have good seeing and you have stable temperatures. So our mirror cooling time is really dependent on thickness. So this is just a rough estimation of it, but cooling time is roughly proportional to the thickness of the mirror squared. So if we have a 1-inch thick mirror, let's just call the cooling time 1, just for reference. Maybe let's call it an hour. We have 1.5 inches thick, it's going to take 2.3 times as long. Just due to the nature of the heat transfer out of a thicker substance, because it's nonlinear, it's got to get out to the air before it can actually get out of the glass. If it's twice as thick, it generally takes about 4 times as long to cool. So this is why I've always worked on as thin a mirror as possible for my clients. And it's about, the 2-inch thick is about 1.8 times the 1.5 inch thick.
Even
So,
with force and convection.
even with forced convection, this is due to the actual heat trying to get out of the glass itself. It has to do with a characteristic distance within the glass. It's a physics thing, but the thickness is the biggest variable.
And the silvering is actually acting as an insulator, so it can only go out the back.
The coating can act as an insulator, not for the whole spectrum. I don't actually know the physics of that, but I'm not sure how much actually deeper IR it blocks, which is where the heat actually, kind of is. But it can make a difference. I just don't know exactly how much. I had a question?
Mike, I'm thinking of how microprocessors are cooled in
Yep.
computers,
Yep.
where they have a heatsink stuck onto
Yes.
the back of them with
Yes.
heat transmission glue.
Yep.
Would there be any merit in sticking one of those
You-
heat sinks onto the back of the secondary or primary mirror?
Now they actually did that for Star Wars mirrors because they're made out of metal. So they put fluid through them to keep them cool, keep them from melting with the laser pulses. For us, that'll just massively distort the mirror, generally, because you'll have something almost adhered to the back and it's metal, so you have a big temperature gradient, like people have done Peltier coolers, but it's going to distort the glass. How much depends on how aggressive you are and the other conditions. It's a physics problem. You can actually calculate it out or simulate it. But yeah, generally we use air because then things behave more uniformly, and I'm going to go into this in a little bit here. So is there a talk right after me at 3?
I believe so.
Okay, I'm going to go as quick as I can then because I want to get to everything here. Our only practical method is air movement. The wind helps. That's another reason this is a good place, because that helps our equilibration of our optics to get them back to their natural shape that they are in a lab condition when things are stable. Forced air really increases the airflow probably about a factor of 10 over passive convection. So it's really necessary if you want to maximize the performance of your mirror. And in the case of professionals, they do that to their buildings as well. They force the ventilation through and cool off the whole structure. To maximize the heat removal, it's really pretty obvious. You want to cool the front and the back of the mirror. Even with the coating, it still works pretty well. I think the coating effect is pretty small. So, okay, yeah, we can cover that later. So we're interested in cooling. We want to simulate a real telescope with a real warm mirror. So I happen to be good friends with John Pratt from JP Astrocraft. He had some old mirror boxes sitting around, and we mocked up a number of mirror boxes with 16, 20, and 24-inch mirrors. Of course, I have unfinished mirrors sitting around. And luckily, I had this 34-inch mirror that was polished out, but it wasn't figured, so it was very nearly spherical. Is anyone familiar with Schlieren testing? Okay. That's when you have a spherical mirror, you have a light source, and you shine that light source on it, it comes back, and you bring your knife edge in. It's like Foucault testing a sphere. What you see is, if you have a good sphere and the air is stable, you see a nice uniform null as you bring the knife edge into the beam. If you have air moving around, you can see that very well, and I'm going to show videos of this. So I'm going to heat the mirrors, do a Schlieren test, which this is just a quick diagram of it. That's a nearly parabolic mirror, but that's what Foucault testing looks like. So I have one mirror with some correction in it. You'll see the shadows, but you can also see the air current superimposed onto it. So what we had, so this is heating up a mirror. Right here, we have this is a fake rocker box with a slot in the side. So imagine you have your mirror pointed at Omega Centauri, but you've got a slot cut in each side, and you can look through it and watch the air moving as fans blow air. It's just an experimental setup to see how much air is each arrangement moving. Here's another picture of it. We've got corner fans here that are blowing from each corner onto a mirror to help, you have some really good turbulence to help scrub off that layer. Turbulence is better for heat transfer than laminar flow. Then we have here, we have the typical boundary layer fans in the bottom and some corner fans, but I have all different arrangements I'll show videos of. Yeah?
Don't the fans in front create some turbulence though?
Yes, that's what I just said. The fans in front create turbulence, but turbulence is good for heat transfer. If you want less turbulence, you turn down the speed. We have speed controllers for fans now. They're cheap. A lot of this involves experimentation. It's telescope specific. So you set up some fans, you adjust their speeds, and you see what works best. It may vary with the night too.
Hey Mike, I'm the next speaker, so
Okay.
we need another like 5 or 10 minutes.
Okay. All right, I'll go as quick as I can here. I think I'm doing okay. So we have a center fan. Thank you, by the way. This is something you may have seen on Joe's 32-inch telescope. He was one of the first to do it. He suspended a fan in front of his 32-inch primary on wires, and they basically are in line with the spider, so it doesn't really add any diffraction. But that thing blows straight at the center of the primary mirror, and then the air spreads out nicely and uniformly and cools the mirror. Of course, he also has a back fan, as typical, because this is a large mirror. Yes, it's a Pyrex mirror. So it will affect things a little bit, but it's going to help that mirror equilibrate. And again, here we want to equilibrate. In the desert is the worst possible place to test an optic out under the sky because the air temperature is dropping so quickly. You actually maximize your distortion. You may use 50 degrees or more over the course of a night. So very difficult to star test. It doesn't work right. Whereas here, we can actually do a little bit of that. So turbulence is good for heat transfer is the main point of this slide. And the Schlieren test will kind of show us how. So I already talked about this 34-inch mirror. Just happened to have it, and I said, okay, it's time to do this test I've always wanted to do. Let's fire up some fans. But first, I want to test the center fan and see just how steady the room was itself. So I'm going to switch to some videos now. And I'm going to try to remember that I'm on slide 27. So let's start off with our first video. These are room air currents. You see the fan suspended there in the center. That's what the X is. That's a fan. It's not running, but we have air currents rising up here. Can you all see that? If you can't see it, get closer. I'll have 10 more of these videos, I think. All right, so this is the baseline. So I decided, okay, this isn't good enough. I'm going to move my experiment to a different part of the shop because, you got windows. They're not perfect. You have air moving around. All right, that's that one. And then I moved it. And this is with a center fan running. Now you notice there's something down there at the bottom making heat. I think I'll talk about that more later on. You can see the little heat plume rising right here. But this fan is running. Okay, and you can't really see too much else going on. Fast forward, there we go. About the same. So now, I'll just stay in this mode for the moment. We didn't see a whole lot going on in that second video because the air is a uniform temperature, and as the fan moves the air, if it's uniform temperature, you don't see it. It doesn't affect the optical performance of the telescope. Just like we have a nice uniform air mass coming across the ocean here, it doesn't do a whole lot to our seeing. So this is a very good thing, but it shows that you can leave a fan running all night and you're not going to necessarily degrade your images. It just depends on what else is going on in the environment. Let's see here. So for this next test, I had a 24-inch mirror and a mocked-up mirror box with side holes. That was a view from the front. That was looking straight down the tester with the camera at the face of the mirror. But now we're going to put that mirror on the other side of the fake mirror box so we can look through and monitor the air movement inside that mirror box using that mirror to reflect it back to us. Okay? So we flip things around. We've got 12 fans total to choose from. I've got 3 80mm boundary layers up top, 3 at the bottom, all blowing upward. So sometimes a typical setup for a certain telescope. I've got 4 80mm corner fans blowing down at the face of the mirror at an angle, diagonally. 1 80mm center fan, as we just saw before, and a larger 140mm rear fan blowing on the rear of the mirror. All of these are going to be fired up at high speed for the video purposes. So here are the videos. We're going to start out with no fans blowing, just ambient. I'm going to get this out of the way. So again, no fans blowing, just ambient. Now this mirror has correction in it. So you're going to see those parabolic shadows, but you're just looking at the changes in the shadows. So you see some air moving here, going up. I'll just step out of the way and let it go. So we've also got the side view right here. So this is a front view. These were different videos, but I merged them together so you could kind of see what was going on. This is the side view. So this is the spot that you're looking through the mirror box, and the mirror is right here on just to the right of it. This white area is the boundary layer of the very warm mirror. Okay, so we're literally looking at both angles at the same time. Now we're going to go to rear fan only. Just the rear fan. So it's moving some air, but on the front of the mirror, we don't see a whole lot going on. You can see the turbulence at the back there. That's the back of the mirror to the right, all the way over here. And this is the front of the mirror. It's just kind of wrapping around a little bit, but it's not doing a whole lot. So typically this is what most people have. It's going to help, but it's not going to be the best possible. So any questions so far? You understand what you're looking at? Front view, and then a side through a fake rocker box with slots cut in it. Okay? We'll let this one time out. Now the next one is center fan only. So we just saw rear fan, center fan only now. Look at that turbulence. You can just see the air going if you get up close enough here. Just a nice radial spread of the air as it's directed at the mirror. And you can see it creating turbulence here. Behind, not much is going on, as we'd expect. Okay? Let that keep going. Again, this mirror has some correction in it. So you see the parabolic shadows, but you can also see the air moving superimposed on that. Now let's see what happens if we've got the rear and the center fan. This is what Joe has. Video number 7 here. And look at that. We've got air mixing on both sides. We've got I think this is a different mirror, but we've got the front kind of cleaned up. I was switching various mirrors through this. This is more efficient heat transfer right here. Both sides of the mirror, both symmetric. This is another important point. There's a center fan and a center fan. You don't have, say, 3 fans blowing on the rear of the mirror. And if you do that, by the way, and it's Supermax or something else, you're going to have triangular stars because you're going to create a weird shape in the glass that's triangular as it shrinks, and you're going to see a little bit of triangularity in the star images.
Does that turbulence go away once the temperature equilibrates?
Yes.
Yeah.
That was what the first video I showed was center fan blowing, but you couldn't see it. Yes, so as the night goes on here, after an hour or two of good cooling, you're going to end up at about 70 degrees, just like the water and the air and the telescope and everything else.
Question. What
Yeah.
will be the direction of these fans? Same or opposite?
The direction of the fans?
Yes.
They're blowing at the mirror. Always directing air towards the mirror to enhance heat transfer. If you're sucking away, it doesn't do much. It can help exhausting warm air out of the top of a large mirror box, but you want to hit the mirror with the air to transfer the heat.
You did heat immediately.
Yes, both blowing at the mirror. Good question, though, if I didn't say that. Now let's try some corner fans. Blowing on the front of the mirror from the corners of the rocker box, so sort of like this. This is doing a really good job. This is better than the center fan. Takes more fans, it's more turbulence, but it works. I mean, look at all that.
So each corner has one fan blowing at the center of the mirror.
Roughly at the center, yeah. Yeah. You could aim them and create a little circulation if you wanted to, but I like to kind of aim them at the same point and let the turbulence happen. Just let it go, because that maximizes. And you can see all that, you know, the boundary layer is pretty much gone. Not a whole lot going behind the mirror back there because there's no fans running. But this is a great way to scrub the front if you don't want to have a fan suspended in the center of your telescope. If you got a large secondary, you can do that. So now we've got a rear fan and corner fans. So probably the most aggressive cooling method yet. Now we're cooking. Even better. Can everybody see this okay? Sorry, I'm trying not to block you, but I have a glare on it I have to see. So, okay. So this is good. I mean, all you've got to do to mount a fan, you need a little bit of vibration isolation. But if you're not running them super fast and they're good fans, it's easy to mount a fan on a bracket in the mirror box and have it kind of directed down, because the corners you have some space. It's not going to get into the optical path. And all these fan speed controls are so cheap now, you can control the speed of every set of fans you want to for not much money. This is the good thing about the computer industry having lots of ventilation. We get better fans. Now let's look at a boundary layer arrangement. So a boundary layer is air going like this or like this in front of the mirror. This is blowing air downward. So we're moving air, but what we also see is that there's more boundary layer down here than up here. So what we're probably going to end up doing is cooling that mirror a bit asymmetrically. So the top's going to be cooler in this case than the bottom. It could be the reverse depending on the direction. So for that reason, I'm not as big a fan of boundary layer fans because they may distort the mirror in certain situations. It depends on where they are. They can hit the edge of the mirror. That's going to start causing some distortion. I actually had some of these in a 16-inch telescope that I built a long time ago, and I got astigmatism from it. So got to be careful. Careful how you implement these things. Now let's have a boundary layer. Let's see. That was blowing downward. Now we're going to have top and bottom. We're going to have one blowing in and one pulling the air out. So in this case, this would keep the warm air from accumulating in the top of the mirror box. And you can just have fans on top if you want that help at first get the hot air out of the mirror box if you have a really large telescope. But this is working pretty well, but we still see there's less of an effect at the top. We have more boundary layer, the bright part, than we do down below. And behind the mirror, there's some stuff going on, but not much. So we still need that rear fan. There's the center fan and the upper boundary layer fans that are exhausting air out to help take the heat out of the mirror box. And this is doing a pretty good job. Actually, John Pratt did this with his 32-inch. He put an array of fans on the top just to help at the beginning of the evening to exhaust air out. And very nice, pretty uniform, lots of turbulence going on, good stuff. Of course, remember the thickness of the mirror. If it's twice as thick, it takes 4 times as long to cool, even with this. We have the corner fans now instead of the center fan, and the upper boundary layer pulling air out. Also a very effective, more effective because you've got 4 times as much air moving within the mirror box.
What effect does the material that the telescope is constructed of have on this? Will aluminum cool faster? In other words, will the structure help
Yes.
cool it versus wood, which is more?
Yes, the wood insulates a little bit the stuff that's inside of it, which in some cases is good because it keeps you from doing up.
Right.
But if you're trying to get rid of the, trying to get rid of heat, the metal will cool quicker than the glass by far, and quicker than wood, definitely.
Second question. You
Yeah.
said that out west, because of the continuing drop in temperature, I remember that somebody had mentioned to me that Kennedy had created mirrors that had deliberate undercorrection.
This is the history of telescopes. There have been undercorrected mirrors for 100 years, and that's what happens when you're trying to compensate for cooling.
Right.
And as an optician, I don't want to create an overcorrected mirror because it'll just get worse.
Right.
However, I don't want to have a very undercorrected mirror. Now, if you're only going to use it in one location and the weather is the same every day, you might be able to do that. But in most cases, you can't. So what I try to do is I try to leave a tiny little bit of undercorrection, but not a large amount. I mean, I've had this problem with the 200-inch hail that has this massive rim. They actually insulated it.
Right.
So insulating the edge of a mirror can help get rid of this problem a little bit. But you still have an overall change of shape that's pretty much unavoidable, and it generally makes the mirror, I'll talk about this right at the end. So you can't compensate. It's basically becomes a weather detector, the mirror does, depending on how much the temperature is changing. But my point was the desert is the worst environment to get a mirror cooled off in because the delta is the biggest. Midwest is pretty bad too. We have, temps to go from 90 down to maybe 70, 90 plus in the summer. So everything's different. An optic is only measurable in the shop, is my point with all of this, for the most part.
There's a question.
Yeah.
Some vendors sell a mirror box that has the fan in the center and the bottom, and then they also have some fans on the side of the mirror box going over the mirror. Is that any good?
In the center of the bottom and on the sides, it just depends on how they're.
Corners.
Yeah.
Just like on the side of the mirror box.
Now, I mean, blowing on the edge of the mirror won't do as much good as kind of getting air flowing around and blowing on the surface, but it's better than nothing. And if there's three of them, that might be a problem. The more you have, the better, because then you don't have that weird distortion when you have like 3 fans or sometimes even 4. So you want more fans is good.
It's done without the mirror support, but the mirror support is actually in the way of those fans.
The mirror support is in the way for the rear of the mirror, but we can't do much about that. It's just what we have to live with. So circulating the air is good. I mean, you can put holes in the triangles. That might help a little bit, but we've kind of, I don't think there's really a massive effect that's created by that. The key is just to have the air circulating. It'll get kind of under those triangles a bit. Yeah. We can only do so much.
Right.
You can always do better, but yeah.
So what would be your recommendation for medium-sized telescope, like 15-inch? What would be?
Medium-sized telescope, rear fan, front fan if you can. Rear fan, diagonal fans if you can in the front. All on speed controls, experiment, see what works the best for you. Yeah. Okay, so we're past that. Now, last few things. We have these little things called fans and speed controllers, and a fan is a motor, so it's transforming electrical energy into motion. And then we have the controllers, which control how much electricity they get. Those both create heat, strangely enough. So we see at a thermal camera, there's a 140 millimeter fan. Here's a 50 millimeter fan. We've got 34, 31 degrees C. Over here, the thing on the right is the speed controller. It's got electronics in it. It warms up. Moral of the story is, you may not want to turn off your fans. Otherwise, you get those weird little rising currents like I showed you before. Here they are. Again, here's the mirror box looking through it. These are air currents from the fans and from the controller. Right there as well. So generally, I like to keep them running at low temperatures. If you're in really good conditions, just keep them on low for once you've done your main bulk of your cooling, and you won't have this problem because that heat will be dissipated. It won't be enough to affect images generally. I mean, it might a little bit, but otherwise you never cool off your mirror. So you kind of have to do it. So to conclude, rear fan alone is ineffective on the front surface of the mirror. You're losing half your cooling capacity, half your heat transfer capability. So a front fan or front fans are encouraged. Boundary layer fans move air. However, it's going to hit one side of the mirror first, so it may cool that side more, causing some distortion. And it's not going to create a lot of turbulence. So it may actually work pretty well, like once you've got things cooled down and you want to do some planetary imaging, it may work fairly well. It depends on the night, depends on the telescope, depends on what's under the telescope. Everything's a variable with this sort of thing. The center fan does affect the entire front surface, unless you have a gale blowing through it, in which case you've got great heat transfer anyways. A center fan is a good thing. The corner fans produce the most airflow because there are more fans and creates the most turbulence, and that'll be the fastest heat transfer. Keep the fans running all night. Turn them down in terms of speed later on if you want, and keep your electronics on top of the mirror box out of the optical path. Mount the fans to minimize vibration and use good quality fans. So here is the actual, this is a a decent illustration that I made of how a mirror distorts due to heat. Where do things cool off from? Their surface. Where is there more surface area? Out here at the edge. That's what I was talking about, insulating the edge. They insulated the edge of the 200-inch Palomar blank because when nightfall came, it dropped by about 2 waves. Because it's that thick, you know, change in dimensions proportional to dimension. So it really rolled off and got a nasty turned edge. So they insulated it. That was one of the first things they determined. Even though it's a cellular blank, still got to do it. I think it was, you know, I don't know how thick that edge is. But this is what happens. So the faster the mirror is cooling, the more distorted it is. Again, it's a weather dependent thing. So your mirror figure is dependent on the weather. Can't do much about that other than try to cool it. This is distorted, but you have most heat here, so that area is going to be larger, and you have least heat here, so that's going to shrink down. So that pulls the edges of the mirror down, which is overcorrection. So that natural tendency to want to undercorrect a mirror if you're star testing, that's where that came from. It's been done by countless people for 100 years. However, quartz helps get rid of a lot of that. So now we can have quite a bit more accurate figure through the course of the night. So I think I covered most of this already. I've measured this at up to a half a wave of effect. It's a lot. And it's concentrated at the edge where most of the surface area of the mirror is. So that messes up the images in a maximum way possible. And that's it. Thank you.